Thanks for coming here today. I'm Alexander Hepp, and I will be presenting our work from 2020 to you. This is the RISC-V with hardware Trojans. To begin with, I'll jump right into how to produce a good ASIC. We were in a lightweight setting during our tape-out. That means we were in the IoT realm, so we tried to get a lightweight design that was flexible and additional, of course, performant, because we wanted to do some post-quantum cryptography on this device, and this is something that needs quite a performance to be operationable in a lightweight design. So if we think about how can we achieve this in a lightweight setting, in a small ASIC, the obvious answer is to do a hardware-software co-design. And hardware-software co-designs are now basically an industry standard to perform such actions, meaning we are co-designing software and hardware together to get optimum performance with additional flexibility. And what we did in our tape-out was an hardware-software co-design for accelerators. Accelerators, in this case, for post-quantum cryptography, that is for cryptography that is resistant to the quantum computer. And for this, you typically need large matrix multiplications, you need hash functions, and there are basically three possibilities to design such an accelerator in a reduced setting. And that is, you can attach these accelerators to the memory bus. This is what we see here in the bottom accelerator. So it's a loosely coupled accelerator where you basically have a memory mapped I/O for this accelerator. The better solution in a constraint device is to go into the pipeline. And there are two possibilities there, basically, depending on how much access or how much data input and output you need for your accelerator. You can do your accelerator in the X stage. In this case, we are talking about a RISC-V 32 device. In the X state of this RISC-V CPU, RV32 may be known to you. And this X stage accelerator, of course, only has access to the two registers that get into the X stage of this pipeline. If we want to have access to more registers of the CPU, because we need more data space, we, for example, have an hash algorithm that has a large state space, then we would want to have a even more tightly coupled accelerator that would be then put into the ID stage already. In this case, for example, we had a catch-check accelerator sitting in the ID stage, so for a hash algorithm to perform on the complete general purpose instruction set, and in addition, in the floating point instruction set, completing then 128-bit of catch-check state space. So after you have decided your accelerator coupling strategy, you of course have to give the design a go. So how to do this, how to design a good accelerator for a lightweight and hopefully flexible situation. You would start by identifying the performance bottlenecks. In our case, we identified that catch-check calculations, that matrix calculations, that sampling of the random ring elements is a performance bottleneck in our design. And we looked into how to solve this. Okay, we have accelerators, and we choose our accelerators appropriately. So in our case, we had a binomial sampling accelerator as an T1 accelerator, so in the X stage, because it doesn't need so many registers. We have a finite field arithmetic in the X stage and in the ID stage, because some of them need quite some registers to represent its state space. And of course, we have the catch-check accelerator, as mentioned already, the hashing function, which really needs a high state space, a large state space, and therefore must sit in the ID stage to get access to all the registers of the device. And after selecting the right accelerator strategy, you would then, of course, think about reusing existing modules in your design. In this case, we have in the X stage, of course, a multiplier, and we can use this multiplier. We do not have to reinvent the wheel there, but use what is there for our matrix multiplications as well. Finally, we, of course, implemented the design for our accelerators, and finally, you want to perform a check if your constraints are actually maintained, if you have improved upon what is there, if you have improved over the software solution, for example, and have a look if everything's fine in the end. So what can we achieve with such an accelerator, such a post-quantum accelerator in a limited setting? We can achieve something like 10 times performance improvement upon software. We can get 10 times faster than a previous solution from our chair that was using a loosely coupled accelerator, so having a high memory overhead, memory transfer overhead, and that improves by 10% to this loosely coupled solution. Finally, we can, of course, also get faster than other solutions. In this case, we had a better architecture and got faster by 7 times compared to a tightly coupled solution that existed already. Of course, we wanted to look for our resources. We were resource constrained in our setting, and fortunately, the area only increased by 10%, while the power was decreasing by 84%. This makes a lot of sense because you need less time for your calculations, meaning less power. Finally, we were actually able to handle this flexibility requirement because there was a new hope. So this is one of the post-quantum cryptography algorithms. There was a change in the specification during the development of the chip, and we could just incorporate this change by changing our software. We didn't have to do any hardware change, just change the software using existing accelerators, and that was already dealing with this new hope specification update. Unfortunately, there was also me in the team of the developers of this device, and I introduced something malicious there. These were hardware Trojans, so malicious entities, malicious parts of the circuit that are meant to disrupt the functionality of the circuit and introduce unwanted functionality to this device. And what happened there is that I was assuming to be an attacker in the IP provider because I was assuming I provided the RISC-V CPU itself and then added a malicious thing. In this special case, I was adding also a malicious compiler because as I am the IP provider, I can also control the compiler, and this leads to much larger attack surface and much better possibilities for developing good hardware Trojans, realistic hardware Trojans. Because, let's have a look. This is all the hardware Trojans that we have in our device, and I will only focus on the most left one, which is a hardware Trojan sitting in the hardware loop controller. A hardware loop controller is basically enabling you to do software loops in hardware, skipping the requirement of a loop control variable, skipping the requirement of pipeline stalls for jumping. This is what was in the device already. And I managed to introduce a hardware Trojan there to break loops early. And this is what we want to look at next. So for setting up the hardware Trojans, you require an assembly instruction. And this assembly instruction can deal with 2 of these hardware loop controllers, meaning you have 2 nested loops in your device for your looping requirements. Fortunately, neither the compiler, so neither the assembler, nor the device itself did note that I can change a bit there, because I can also say, okay, there is a 3rd hardware loop controller there, and I want to set up this 3rd one, which is not in the hardware. That means that we have now a covered channel from the compiler to the device. I have 1 bit. I have even more bits to spare, but I only needed to use 1 bit. And we have a secret channel from the compiler to the hardware, enabling me to say, okay, I use the compiler to determine which hardware loops are interesting to break early, notify this to the hardware across this secret channel, and the hardware then breaks these loops early. And finally, what can I achieve with this? I can achieve a hardware Trojan that is much less complex. It only has basically half of the cells that you would need for a standard hardware Trojan disabling cryptography. I had one in this device too. You have much simpler activation function, meaning that you would have much harder time to find this by looking at the possible activation function in your design, which is a typical hardware Trojan detection techniques that you look into the device, look what possible points of hardware Trojan insertion are there. You won't find this because it's so simple. And in addition, you have no side channel activity because basically there is only 1 gate that checks if this bit is set, and you can't find that with the side channel. Finally, fortunately, in our case, there were some indicators that made sure that we actually could find this hardware Trojan in the real case, which brings me to my last slide already, which is the conclusion. I want to highlight that hardware-software co-design enables perfect, efficient accelerators, but also it enables efficient hardware Trojans. We can show substantial performance improvements, but also substantial problems in detecting the hardware Trojans that are using this approach. Additionally, what I will give to you as a takeaway is that you want to measure your bottleneck to find out the spots where a hardware accelerator and hardware-software co-design make sense. You want to mind the overhead that might be in some memory transaction, so choose the right accelerator strategy. And for hardware Trojan detection, there is a requirement for defense in depth. You have to verify that each step of your tape out is hardware Trojan free. It's not enough to just check at the end if everything is fine. You want maybe to formally verify your design. This is something that is really going in the RISC-V development at the moment, that we have formally verified cores which must not have hardware Trojan, cannot have hardware Trojans because it was formally verified that there is nothing else than the specification. And finally, what I am doing is reverse engineering then such circuits to additionally verify that at the end of the development cycle, at the end of the supply chain, there is actually no hardware Trojan in there. This was it for today. Thank you for your attention, and I'm open for questions.
All right, all right. Get those questions started online. I'll absolutely read those. If we don't have any questions, let's look around the room here. See if there are any questions in the room. I'd be happy to repeat those for you, you going to the virtual channel. Questions? Deeply interesting and deeply concerning all at the same time.
That is true.
No questions around the room? No questions online? I guess it was clear. So thank you very much, Alexander. Let's give him one more round of applause.